Linear Regression in R. My name is Richard Kirschner with the Simplilearn team. That's www.simplilearn.com. Get certified, get ahead. What's in it for you? We'll start with covering why linear regression, what is linear regression, how linear regression works, and then finally we'll dive into the use case predicting the revenue using linear regression. And we'll be in the R platform for this today. Let's dive into why linear regression. Now that we have come this far, I'm planning to take a closer look at our cells so that we can estimate cells in the future. How about we hire a data scientist? You can see our two corporate individuals. It looks more like they should be agents or secret agents someplace, discussing how to better forward their company. And so they're going to come in and ask the data scientist to come in. Good idea. This will help us to keep a constant track of our cells. So why do we need linear regression? Let's assume that we need to predict the number of skiers based on snowfall. So this happens to be, we've kind of jumped one business to the next. So we're looking at the skiing business, very popular in a lot of areas. And it's based on snowfall a lot of times. You figure you don't have snow, you don't have skiers. But can we actually use something more specific instead of, look, it's snowing? And instead of saying, hey, look, it's snowing, we can actually start drawing graphs. And the graph shows that with an increase in snowfall, the frequency of skiers also increases. So, and there's a pretty direct correlation. If you've ever been up to the ski areas, when there's a lot of snowfalls, the skiers all show up because they know it's going to be better skiing right afterward. So it's kind of easy to see why skiers and snowfall would go together. And it usually draws a nice straight line. And you can easily predict how many skiers, and that way you can also predict how many people you need to service them, how many lifts to have up and running, and all the stuff that goes with running a ski area. Thus, we see that the number of skiers are directly proportional to the amount of snowfall. Regression models a relation between a dependent y and an independent x variable. This is real important to understand regression, because when we talk about linear regression, it's the basis of almost all our machine learning algorithms out there, and it's usually an underlying part of the math in our deep learning. So it all starts here with linear regression. And when we talk about a dependent y and an independent x variable, these are numbers. We're usually talking about floats. So we want to have an actual number value coming out. And that's different than something that's categorical, where we want to know yes or no, true, false. So regression means we're looking for a number. The independent variable is known as predictor variable, and dependent variable is known as the response variable. So we have one predictor variable, the amount of snowfall, and one response variable, how many skiers are going to show up. And then we can take this relationship and it can be expressed as y equals beta. We're going to use the Greek letter beta, and we have beta naught plus beta 1 x1. And if you continue out, it'd be plus beta 2, x2, and so on till the nth degree. In this case, snowfall is an independent variable, and skiers is a dependent variable. So we kind of had a little quick overview. Let's go ahead and talk a little bit more about what is linear regression. So we're going to go from y, predicting a number of skiers for snowfall, and we looked at the formula a little bit, but let's look a little bit closer at what exactly is going on with linear regression. And the question is going to come up in an interview. What is linear regression? Linear regression is a type of statistical analysis that attempts to show the relationship between two variables. Linear regression creates a predictive model on any data showing trends in data. The model is found by using the least square method. There are other methods. The least square method happens to be the most commonly used out there. And we usually start with the least square method since it's the most common and usually works the best on most models. And we're already looking at how linear regression works, but let's dig deeper into it and let's take a closer look. How linear regression works. I will provide you with a data set which has rent, area, other information in it. It looks like our secret agents have put on their casual wear for this one. You need to predict rent accordingly. We are given area and rent here. So you can do linear regression with more variables, but we're just going to look at the area and then from that try to figure out what the rent should be. We plot the graph. And if you look at it here, you can see that the graph is kind of a linear pattern with a little dip in it. So the rent seems to be based on the area. In most of our work as data scientists, we usually try to start with a physical graph if we can. So we can actually look at it and say, hey, does what I'm fitting to this graph look right? You can solve a lot of problems that arise by looking at the graph and saying, no, that doesn't look right at all. Or, oh, I should be looking over here for this. Then we find the mean of area and rent. So the mean just means average, and if you take 1, 2, 3, 4, 5 and add them all together and divide by, in this case there's 5 areas, you get 3. And the rent is 2, 4, 6, 5, and 8. If you add them all together and divide by 5, you get 5. And we plot the mean on the graph. So you can see right here, here's the mean of the rent and the area. It's kind of a very central point, which is what we're looking for, the average of everything in there. The best fit line passes through the mean. This is real important. When you're eyeballing it, as humans we can do this fairly easy if it's a straight line through a bunch of data. It gets more complicated mathematically when you start adding multiple variables and instead of a line you have a curve. But for basic linear regression, we're going to draw a line through the data, and the line should go through the means. That's going to be part of the best fit for that line. But we see there are multiple lines that can pass through the means. So depending on how you look at it, you can kind of wiggle the line around back and forth. So we keep moving the line to ensure that the best fit line has the least square distance from the data points. And this is, you can see right here, residual. We have our data point, and then we look at this distance between them, and we square that distance. And that's what they mean by the least squared distance. We want all those distances to add up to the smallest amount we can. When we talk about that distance, we call it the residual. It equals the y actual minus the y predicted. Very straightforward. We're just looking at the distance. You can accidentally switch these, and it'll come out the same because we're going to square it. But when you're working with other sets of linear regression, you want to make sure you do the y actual minus the y predicted. The value of m and c for the best fit line, y equals mx plus c, can be calculated using the mentioned formula. And you can see here we have m equals the number of points, that's what n stands for. Then we have the sigma, the Greek symbol is there, which is a summation of x times y minus the summation of x times the summation of y over the number of the summation of x squared minus the summation of x squared, of x, all of it squared. That can be a little confusing trying to say that. And then of course your c value is going to be the summation of y times the summation of x squared minus the summation of x times the summation of x times y over the total count of the summation x squared minus the summation of x squared. That's a mouthful. Normally we don't worry too much about these formulas other than to know they're there. Now if you're a mathematician, you might go back in there and work on those. And those people who originally started to put together the different models in R, of course, had to know all this math to build them and had to test it out. That's one of the nice things about R. What is important is that you know about these formulas so that you know where it's coming from. So if you're using one linear regression model, this is how this one works. There's other linear regression models based on different math. And so you'd have to be aware when that math changes and how that changes the model. We find the corresponding values. So in this case, if you're going to break this up and you're building your own model instead of using the one in R, you would have your rent, you would have your area, you would find your rent squared, your area squared, and your rent times area. And if we go back one, we can see that that's all the different little pieces in this model. We have x times y, we have x squared, we have the sum of x, which is going to be squared, we have the sum of x, the sum of y. This is the same. These are all the little pieces in here that we see for m equals and c equals. And so once we compute all these, we have 15, 25, 55, 145, 88. Very easy to do on a computer, thankfully. You could have millions of these points and it would do it in a very short period. We can then plug in those values very easily into this formula and get a final answer. And we'll see that m equals 1.3 and c equals 1.1. And then when we take this for the y predicted equals m of I, x of I plus c, we can take these and actually run the data we have. So we're going to see how it predicts. So now we find the value of y predicted. So we have our xn, and we want to know what we think y will be based on our formula we generated, the linear regression formula. And so when we come in here, we have our x, we have our actual y, then we have our y predict, what we think it's going to be. And then we have, we take y minus y predict, and we get those values, minus 0.4, it's off by 0.3, this one's off by 1, this one's off by minus 1.3, by 0.4. And we go ahead and square that, and then we can sum that square and average it out, and we'll get a value. This is just a summation down here of y minus y predicted square is 3.1. And we call that the least square value for this line is 3.1, and we go ahead and divide that by 5. So when we plot the y predict, and this is the best fit line, and you can see that it does a pretty good job going right through the middle of lines. And in something like rent versus area if you're trying to figure out how much rent to charge or how many people are allowed to be in the area that's going to work. But if you're looking for the rent value compared to the area, this gives you a good idea based on the area of what you should rent the place for. It's close enough that in the business world this would work. You're not computing something down to the millimeters or micrometers or nuclear physics. We're just charging people, and so if you're off by a couple of dollars, it's not a big deal. You'll be pretty close to what you think it's worth and get the right value for your property. Use case: predicting the revenue using linear regression. Now that you have a good idea of how linear regression works, and we're kicking back on our lounging sofa today, let's work on a real-life scenario where you have to predict the revenue. So we're going to take a data set, and we'll pull this up in just a minute. We'll have paid, organic, social, and revenue. There are 3 attributes we'll be working on. The first one is our paid traffic, so all the traffic through the advertisement that comes in. The non-paid traffic from search engines. So these are people coming to the website and are doing so because they did a search for something specific, so it's pulling it from your website. All the traffic coming from social networking sites. So we want to know what's coming from Twitter and Facebook, and somehow they've linked into your website and coming into your marketing area to buy something. And we'll use this to predict the revenue. So we want to know how all this traffic comes together and how it's going to affect our sales if the traffic's coming in. We're going to make use of the multiple linear regression model. So you'll see that this is very similar to what we had before, where we had y equals m times x plus c, but instead we have y equals m1 x1 plus m2 x2 plus m3 x3 plus c. M is the slope. So you have M1, M2, M3, the 3 different slopes of the 3 different lines. Y is the revenue, so we're only looking for one variable. And remember, this is regression, so we're looking for a number. X1 is going to be the paid traffic, and of course M1, the corresponding slope. X2, the organic traffic, and X3, the social traffic. We will follow these steps to create the regression model. We'll start by generating inputs using the CSV files. We'll then import the libraries, splitting the data into train and test. Very important whenever you're doing any kind of data science. Applying regression on paid traffic, organic traffic, social traffic. So we're going to apply a regression model on them. And then we're going to validate the model. That's the whole reason we split it to a training and testing, is so we can now validate to see just how good our model is. Now before we open up R, I always like to just take a quick look at the data itself, and we're using the rev.csv file, and this is a .cs file or a comma separated variable file. We'll just open that with WordPad. Any kind of text editor would be nice to show you what's going on. And you can see we have paid, organic, social, and revenue across the top, so those are your titles for your columns, and the values going down. And this is the same as what we saw on the slide just a minute ago. Paid, organic, social, and then the revenue from them. They probably have it in more of a spreadsheet than just a WordPad. And I'm using the newer version of RStudio, which already has a nice layout. It automatically opens up with your console and terminal window down and left. You have your script, and we'll run it in script, and then when I run it line by line in script, you'll see it show up on the console bottom left. I could type it straight into the console and it would do the same thing. And then on the right we have our environment, and under the environment we'll see plots. If you're in an older version, the plots will pop up, and you usually are running just in the console, and then you have to open up a different window to run the script, and you can run the script from there. This opens up everything at the same time when you use the new RStudio setup. And the first thing we want to do is we want to go ahead and generate a variable. We'll call it cells, and we want to load this with our data set. And so in R, we use the less than minus sign. That's the same as assigned to. It's like an arrow pointing at cells, and it says whatever it goes past here is going to be assigned to cells. And we want to read in our CSV file. And then I went ahead and fixed the CSV file up a little bit. When I say the CSV file, I mean the path to it. And we'll go ahead and just paste that in there. And this is my edited version. And you'll see I took wherever we had the backward slash, I switched it for a forward slash, because a backward slash is an escape character, and whenever you're programming in just about any scripting language, you want to do the forward slash instead. So like a good chef, I prepped this and copied it into my clipboard, and we can see the full path here, and the full path ends in our rev.csv file. So that's the path on my machine. And then I'm going to run that, and now we have down here, you see it appear right here. Uh-oh, I must have an error in my path. It says object rev not found. Let me fix that real quick and run it again, and this time it does assign the cells the data set, and then we'll just type in cells, and this is the same as printing it. So if you work in other languages, you'll do like print and then cells, or maybe print cells.head if you're in pandas in Python or something like that. But in R, you just type in the variable. We'll run this, and you can see it printed out all those columns. So that's the same thing we just looked at. And it says max print, so it omitted 750 rows, so it has a total of 1,000 rows. And we can scroll up here on our console where the answer came in. And if I scroll up to the top, way up to the top, there we go, you'll see paid, organic, social, and revenue. So everything looks good on this. And then there's a lot of cool things we can do with it. One of the things we can do is I can summary it. So let's do a summary of cells, and we'll run that. And the summary of cells comes in. It tells you your min, first quarter, median, mean, third quarter, max for paid, organic, social. Breaks it up, and you can actually get kind of a quick view as to what the data is doing. You can take more time to study this. A lot of people look at this, and you can see from the median, the mean, that tells you a lot. And it's divided into quarters, so you have your first quarter value and your third quarter set up on there, and max. It just gives you a quick idea of what's going on in the data. The summary is a really wonderful tool. One of the reasons I like to jump into R before I might do a major project in something else, or you can run everything in R. And let's take a look at the head of cells, and let me run this. And you can see it just shows the head of our data, the first 6 rows in this case, and it starts with 1. Important to know, other different systems start with 0 and go up. R is one that starts with the first as 1. And then if we want to do a plot, I'll go ahead and do a plot cells. Another really powerful tool that you can just jump right into with R once you have your data in here. And you'll see that the plot comes over on the right hand side. And what it does is it compares them. So if I look at my paid and my organic, and you cross the two, you'll see there's a nice line down the middle, big black line where it plots the two together. Let me just widen this a little bit so we can see more of it. There we go. The same thing with paid and social, paid and revenue. So each one of these has a clear connection to each other. So that's a good sign. We have a nice correlation between the data, and you can just eyeball that. That's a good way to jump in and explore your data rather quickly and see what's going on. So we'll go ahead and I'll put a pound sign there. Hashtag, and splitting the data into training and test data. And we want to split it so that we have something to work with to train our data set. And when we do our data set, you do this with any data set because you want to make sure you have a good model. And then once we've trained it, we're going to take the other set of data we pulled off to the side and we'll test it to see how good it is. If you test it with the training data, it's already got that memorized and should give you a really good answer. In fact, when you get into more advanced machine learning tools, you watch those very closely. You watch your training set and how it does versus your testing set. And if your training set starts doing better than your testing set, then you're starting to overtrain it. Now that's more with deep learning and some other packages that are beyond what we're working with today. But this is important. It's very important to understand that that test and that training correlate with each other and gives you an idea of what's going on, and make sure that you're set up correctly. And we'll go ahead and set a seed of 2, and that's for our random generators, so that when we run them, you could seed them with just there's ways to randomize a number. You could do like date and stuff like that. But that way we always use the same random numbers. So we'll seed it with 2. And then we're going to need a library. In this case, we're going to import the library, and we want to import CA tools. And CA tools has our split function, so we're going to be able to split our data, along with many other tools we're going to need for this example. So they're all built into the CA tools. That's why we need to import that. A lot of times they call them library, or sometimes you hear them referred to as packages. So let's go ahead and run that line. And that brings the library in, so now we can use all those different tools that are in there. And then I'm going to do a split. And we're going to assign to the split, that's going to be our variable, sample split. Okay, so that's one of the tools we just brought in, is to sample is the actual keyword or the function word, sample.split. And we're going to take our cells and we're going to go ahead and do a split ratio equals to 0.7. And let's do 0.7 so we make sure it knows it's a decimal point or a float. And what this is saying is that we're going to take our cells data, the variable we created called cells that has the data in there, and I want to split it, and I'm going to split it so that 70% of it goes in one side. We'll use that for training, and 30% will go into the other side, which we'll use then for testing out our model. Let me go ahead and run that. And oops, hold on one second. Got an error there. Spit is definitely very different than split. I don't think we want to spit our data out, which is actually kind of what we're doing, is spitting it out. But we want to split. We want to split the data. So let me get that spelled correctly. And then when I type in split, we can just run that because that's now a variable. You'll see that it has true, false, false, true. So it generates a number of interesting different statistics going across there as far as the way it splits the data. And right here, if you have not used R in a while, or if you're new to R completely, that line 1, that's what that little 1 means down there, and then true, false, false, true. That means that's how we're looking at the data. We're splitting all those different pieces of data in line 1 different directions. And so we now want to create our train set, and we're going to assign that. And when we take it and we assign to the train set a subset of cells, and then the subset of cells is going to be based on split equal, I put this in brackets, true. So you can see the values down here is capital T, capital R, capital U, capital E. So I just want to reflect that on the train. And this is going to take everything where our split variable is equal to true, and it's going to set cells equal to that. And we'll go ahead and run that. And then we're going to set our test variable as a subset of cells, and if we assign the true to the train set, then we want to assign the false to our test set. So now we'll have this will have 30% of the variables in it, and train will have 70%. We'll go ahead and run that. So we've now created both our training set and our test set, and we can just real quickly type in train, hit the run on there, and you can see our train set. If we scroll way up to the top, we'll have the column names on there, which should match what we had before. Paid, organic, social, and revenue. And then we'll type in test. When I hit run on there, that's going to do the same thing. It'll spit out all the test variables going out. So now that we have the test and train variables, we want to go ahead and create the model. And you'll see this in any of the machine learning tutorials. They always refer to them as models. We're modeling a function of some kind on the data to fit the data, and then we're going to put the test data through there to see how well it does. And so we're going to create the variable called models, and I'm going to assign that LM, that is our linear regression model. I love how simplified R makes it, just LM, linear regression, and then model, M. I guess it dates back because the linear regression model is like one of the first major models used, so they kept it easy on there. And revenue happens to be the main variable that we want to track. So if you remember correctly from our formula, Y is the revenue, and then we have X is our paid traffic, X2 our organic traffic, and X3 our social traffic. So Y is what we want to predict in here. And then you'll see this notation where we have our squiggle and the period, which means we're going to match up the revenue lines with the lines of the data we're putting in here. And then I'll put comma, and then our data equals train. And of course that's the training data that we created. So when I hit the run, remember we did all that discussion about all those different functions and formulas to compute our model and how that's set up. When it comes down to it, we spend all our time setting up our data, and then I hit the run button on the single line, and our model's been trained. So we now have a trained model here. And we can do a summary of the model. Summary is such a wonderful command because you can do that on R. That works on all kinds of different things on there. Oops. And of course it does help if I remember that my model has a capital N when I run it. And you'll see right here, it tells you a little bit about the model. Use a summary on there. Comes down here, it has our residuals. This is all the information on there as far as like the minimum, the median, the max. It has all our coefficients in there. If you remember correctly from our formula, let's just go ahead and switch back over to that. We have M1, X1, M2, X2, M3, X3 plus C. Well, that's right here. Here's our intercept, and then we have our different values for each of these. So you have our intercept, our paid, organic, and social. And then it also shows us error and information on the error. And one of the really nice things about when you're working with R, you can come down here and you see where we have our stars down here, and it says 3 stars, really good. 2 stars, maybe. 1 star, probably no correlation. And we can see with all of these, it has 3 stars on them. So out of 3 stars, we get 3 stars on all of these. There's no 4 stars. 4 stars would mean that you have the exact same data going in as coming out. And then if we're going to do this, we want to actually run a prediction on here. And that's what we saved our test data for. So let's come down here, we'll do our prediction. We'll take this variable and we'll assign it predict model. And remember, the predict comes from when we imported that package, the CA tools. That's all part of the CA tools in there. So we're going to predict, we're going to use the model, and then we're going to use our test data. Pretty straightforward, quick and easy. We'll run this, and then if we go ahead and type in the predict, it'll print out what's in that variable, and you'll see down here the predicted values it expects to come out. It's going to say our revenue is, and it goes through and it gives it both the line number and the actual revenue value. So that's quick and easy. Boy, we got a prediction really fast. And this is also how you would do it if you had new data coming in after this. You could predict the revenue based on these other factors. So now that we have a training model, or we trained the data with our training data, or we trained the model with our training data, and we've done a prediction on our model with our test data, we want to look this up, and we took a quick glance from our training thing. Our training said it trained really well. But that's not the final word on it. The final word is going to be comparing it. So we want to go ahead and we're going to do comparing predicted versus actual values. What I'm going to do is I'm going to do a plot, and I'm going to do our test, and we're going to do test revenue.type equals, and we're going to put this in as a type 1 and then, or L, and then we have LTY equals 1.8, and we're going to set it up for column blue. That's a lot of stuff in there. Let's go ahead and just run that so we can see what that looks like and what's that's doing. It's going to generate this nice graph we see on the right. There's our graph. You can see the data comes up and down. We're plotting the prediction on there, so this is the values we predicted. And then let's go ahead and do lines. And I actually did this backwards, so let me try that again. And we'll start with the red one. We're going to do the first one in red. And I want to start with the actual test revenue. So here's our test revenue, and we'll go ahead and run this. And so we have our red plot over here in red. Go ahead and take a look at that. Pull that over, you can see how that looks. It goes up and down, hard to track there. And then we're going to do a couple things here. We'll plot our test revenue. And then we'll make it a little pretty, although it's kind of hard to see the way I have it scrunched up here on the right as far as size and sizing and everything. But we'll go ahead and have our columns in blue and run our prediction on there too. And you can see they overlap the two graphs. So we have our test revenue and our prediction. And then finally, what I started with is we'll go ahead and plot the prediction fully on the bottom and run that. And if you look over here on the graph, we put the blue lines over the red lines. And so you'll see a couple spots where there's red underneath there, but for the most part, our prediction's pretty right on. So it looks really tight. It looks like a good set of predictions for what we're working on. And this is what we were looking at the slide right before we started diving into the RStudio. We can see in the slide here, here's a red. This is a little bit better spread out than what I have on my screen for my RStudio. And the graph shows the predicted revenue. We see that the two lines are very close. So again, they're tight. It's right on. This is what we're looking for in our prediction model. But it's not good enough just having a graph. You always do both. And the reason we do both is you want to have a visual of it, because sometimes you look at these and you get to the graph, you're like, oh my gosh, what is that? And then sometimes you look at the graph and go, that's right on. How come my accuracy doesn't look right? And you realize that your accuracy might be off, or you're plotting it incorrectly. So let's go ahead and look at the accuracy. And we'll use RMSE. That's going to be the variable name we're going to give it. And SQRT, the square root of the mean, and mean just means average. And then we want prediction minus sales revenue, and then we're going to take this whole thing and we're going to square it. So what we've got here is we're going to go through, and let's just explain this formula we're using. Is I'm going to look at what I predict it for to be and what the actual sales, what's our prediction versus our sales in comparison to the revenue. And when we compare those two, we're going to find the average, and then we're going to square each one of those values, and then we're going to average the square and then find the square root of that. And that's quite a mouthful. The reason we do it this way, the reason we square the value and then we find the means, is to generate an answer based on, doesn't matter whether it's plus or minus. And there's a lot of other formulas you can use there to check your accuracy and all kinds of other things you can do. But a quick, straightforward way of doing it is just like this, and then let's go ahead and run this. And then we type in the RMSE, and that'll give us an actual printed value out. Let's just see what that looks like. And so we have 866.6338 for our accuracy. And so when we look at the 866.63 and we compare that to, say, 50,000, that's pretty close. That's actually a pretty good accuracy given this model. It takes a little bit more when you're playing with accuracies and start dividing out other different aspects of it to get something you can communicate better with. But you always start with the square root means. That's always a good place to start. So what are the key takeaways for this? Why linear regression? Regression models a relationship between dependency y and an independent x variable. The independent variable is known as a predictor variable, and the dependent variable is known as the response variable. The relationship can be expressed as y equals beta naught plus beta 1 x1 plus beta 2 x2, etc. And we looked at what linear regression is. Linear regression is a type of statistical analysis that attempts to show the relationship between two variables. Linear regression creates a predictive model on any data showing trends in data. The model is found by using the least square method. And then we looked at how linear regression works. We plot the y-predict, and this is the best fit line, whatever is going to have the minimal error on it. And use case to predict the revenue. We looked at being able to generate a model that allows you to predict a revenue. Now, a lot of times when you're studying machine learning and you get into deep learning or any of the other models, almost all of them have some math based on this linear regression model. This is the basis of so much. And if you're starting with any new data, this is a good place to start because it helps build a very solid function you can look at and usually can predict a lot of things. Or you can take this prediction and put it into your next step, which would be to look for outliers, things that don't match the linear regression model, and find out why, and find out other information about those areas so you can better predict them. In which case, we'll wrap up our linear regression model in R today. Thank you for joining us. For more information, visit www.simplilearn.com. Get certified, get ahead.
Hi there, if you like this video, subscribe to the Simplilearn YouTube channel and click here to watch similar videos. To nerd up and get certified, click here.